Hello friends, today this is part 1 for the year 2022 and we are going to solve 17 questions, and all these 17 questions are from the mains. So in the first question, it states that a spherically symmetric charge distribution is considered with a charge density varying as rho r given as rho naught 3 by 4 minus small r divided by capital R when r is less than equal to capital R, and it is 0 for r is greater than r, where r is the distance from the center O as shown in the figure. The electrostatic potential at point P will be. So basic figure is given to us. We have to find out electrostatic potential at this point P, which is at a distance of r from the center, and the point P is inside the, you can say, the sphere or shell. And so we are given that our charge density, which is our rho of r, and it is equal to rho naught 3 by 4 minus r upon capital R, and this is condition is true when small r is less than equal to capital R. So it means for any point which is inside the sphere, we are going to find out, or we are going to take the charge density by this equation, and it is 0 for any point which is lying outside the sphere. And for here we are going to use the Gauss law in order to find out our electric field. And in Gauss law we already know that integration of the electric field small area will be equal to our charge enclosed divided by epsilon naught. So we are mainly interested in this charge enclosed, and this charge enclosed we are going to take with respect to point P or radius r. Therefore we can say that the charge enclosed, we call this as Q enclosed, within the Gaussian sphere of radius r. Gaussian sphere of radius small r, and that will be equal to over Q enclosed is equal to integration from the center to the point P, and this we can write rho as r prime, and this will be coming as 4 pi r prime whole square, and this is our dr prime. Okay, we have taken this dr prime, another variable, in order to differentiate from the Gaussian radius. That's the only purpose of that. Otherwise it is the almost synonymous to the radius. And so we can just substitute value of our charge density. We get this as 0 to r, where this is rho naught 3 by 4 minus r prime upon r, and multiply by 4 by r prime whole square and dr prime. And we can take common as our 4 pi and rho naught. So if this comes as 4 pi rho naught integration 0 to r, and this comes as now 3 by 4 r prime whole square minus r prime whole cube divided by capital R, and this is our dr prime. Now we are going to simply integrate it, and we get from here as 4 pi rho naught. This will be our 3 by 4 r prime cube divided by 3 minus r prime 4 divided by 4r, and limits are from 0 to r. We substitute the limits, and here this 3 and 3 cancels out, so we get this as 4 pi rho naught. It will be coming as our r cube by 4 minus r4 divided by 4r, and we can take our r cube by 4 as common, so our this 4 and 4 and this 4 goes away, and we get our, this will be equal to rather pi rho naught r cube 1 minus small r divided by capital R. Now we are going to use Gauss law because we found out the charge enclosed. Therefore we can say that Gauss law for enclosed surface, our electric field is equal to Q enclosed divided by epsilon naught, and we can write this as our electric field. It will be, area will be coming as 4 pi r square. Q enclosed is our, we can write this as 1 upon epsilon naught pi rho naught r cube. This is 1 minus small r divided by capital R, and here this r cube, pi and pi goes away, and we get our electric field will be equal to our rho naught, sorry, one second, r square. Yes, it's r square, not r cube. So this square cancel out with this cube, only one r is remaining, so we get this as rho naught r divided by 4 epsilon naught, and this comes as 1 minus small r divided by capital R. So this is our electric field. So we can say our option number C is the correct one. Option C is correct. Next question. It states that a wire of length 314 centimeter carrying a current of 14 ampere is bent to form a circle. The magnetic moment of the coil is. So we are given a wire, and his length is given as 314 centimeter, and it is bent to form a circle. And let us suppose R is the radius of the circle. So length of the wire will be equal to our circumference of the circle. Therefore we can write that length of wire is equal to circumference of circle, which gives us length is our 314 is equal to circumference is our 2 pi r and from here we can write our r will be equal to 314 and divided by 2 into 3.14, which gives us 100 divided by 2, radius is our 50 centimeters. And we need to find the magnetic moment. We know our magnetic moment, that is represented as small m, is equal to our I and area. We can easily find out area will be equal to pi r square. So we substitute it, we get our magnetic moment is equal to our I and pi r square. Current is given to us as 14, pi is our 3.14 and this comes as 0.5 whole square. So our magnetic moment approximately will be coming as 11 ampere per meter square. So this goes as 11. Next question. We are given two identical metallic spheres A and B, when placed at certain distance in air, repel each other with a force F. Another identical uncharged sphere C is first placed in contact with A and then in contact with B, and finally placed at midpoint between spheres A and B. The force experienced by the sphere C will be. So here we are given basically three spheres, A, B and C. Both A and B are charged, but C is initially uncharged. Then it is brought in contact with A and second part in B. Then C is placed in between A and B, midpoint. So we can just say that we have two spheres, A sphere and B sphere, and they are identical with each other, and they are repel each other. So let us suppose A is having a charge of plus Q and B is having a charge of also plus Q initially. So this is our initial condition. And if r is the distance between them, then the force of repulsion, which is our F, given F, will be equal to 1 upon 4 pi epsilon naught, and this comes as our Q square upon R square. Then we come to our final condition. Final condition. In final condition, another sphere C, which is also identical with A and B, is brought in contact first with A. Okay, so it is in contact with A, and initially the charge on C, let us suppose that QC is equal to 0, and charge on A, that is our QA, is equal to plus Q. So this is our QA and this is our QB. And after contact, they will be at the same potential, and everything is same between A and C, so charge will be accordingly equally distributed between them. So in final condition, the charge on C, that is our QC, will be equal to plus Q by 2, and charge on A, which is our, let us suppose, our QA prime, will be also our plus Q by 2. And after that, this C is brought in contact with our B, and B is having a initial charge, that is a QB, is equal to plus of Q. Therefore, the charge between B and C, this will be coming as B will be having a charge of our 3Q by 2. Let us suppose this is QB prime, and our C, that is our QC prime, will be having a charge of 3Q by 2. So it means finally we can write that final charge on A will be our plus Q by 2, on B it is our 3Q by 4, and on C it is 3Q by 4. All are positive. So these are the final charges on our A, B and C. Now in the question it is given that the charge C is placed in between at the midpoint of A and B. So let us suppose we have, this is our A and B, and R is the distance between them, and we placed C, which is in between them. So we are going to have R by 2, and here also our R by 2, and all charges are positive. So obviously B is going to repel charge C toward left, and A is going to repel charge C towards right. So let's find out the force on C due to A. Force on C due to A. FAC will be equal to our K times, we have this as QC prime, and QA prime divided by our R by 2 whole square. We get FAC will be equal to K, and our QC prime is our 3Q by 4, and QA prime is our Q by 2, divided by, this will be coming as R square by 4, and our this 4 goes by 4, so we get this as our K. This will be coming as 3 by 2 R square, and we have here Q square. Similarly, we can find out force on C due to A. Force on C due to A, let us call this, due to B. Let us call this FBC will be equal to our K. This is our QB prime multiplied by QC prime divided by R by 2 ka whole square. We substitute the value, we get this as FBC will be equal to K. QB prime is our 3Q by, both are same. So we can write this as 3Q by 4 whole square divided by R square and 4. This will be giving us K, and this 4 goes by this 4. This is 16 and 4, so we are left with this as 9 Q square, and here we have 4 R square. Now both forces are in opposite direction, therefore we can say net force let us call that as F will be equal to FBC minus FAC. So our BC was our K9 Q square upon 4R square minus K 3 by 2 Q square upon R square, and we can just take common. This gives us, we have K Q square upon R square, and we are left with 9 by 4 minus 3 by 2, and our initial force F is our Q square upon R square. So here we can just substitute this particular by our F, and 4 will be LCM, so this comes as 9 minus 6, and we get our, let us call this F net. So we can say that our F net will be equal to 3 by 4 times F. So we get this as 3 by 4 times F. So option B is correct. Next question. We are given that two identical thin metal plates have charge Q1 and Q2 respectively, such that Q1 is greater than Q2. The plates are brought together close to each other to form a parallel plate capacitor of capacitance C. The potential difference between them is, and here we are given that we have two plates. One is having a charge of Q1, another is having a charge of Q2, and they are brought together but not connected. Okay. So therefore we can say that effectively one plate is going to act as a positive and another plate is going to act as a negative. And this effective charge distribution is going to result in the electric field and hence the potential difference. So therefore we can find out that effective charge, you can say effective charge contributing to the electric field and potential difference let us suppose that is written as Q. So this Q will be equal to Q1 minus Q2 divided by 2. Okay. And effectively the plate which is having a higher charge effectively becomes positive and the lower charge effectively becomes negative. So we can say that the effective charge on each plate effective charge on each plate, we are going to have one side will be positive and its magnitude will be Q1 minus Q2 divided by 2, and other plate will be negative and effective will be magnitude will be same. Okay. Or we can say this will be our plus of Q and this will be our minus of Q. Now we can just use that for a, you can say, capacitance. We know that potential difference across a capacitor, that is our V, will be equal to our charge divided by C, and we substitute value of Q, which is our Q1 minus Q2 divided by 2C. So this is the effective potential, Q1 minus Q2 divided by 2C. Option C is correct. C is correct. Next question. Given two capacitors each having capacitance 40 microfarad are connected in series, the space between one of the capacitor is filled with dielectric material of dielectric constant K such that the equivalent capacitance of the system becomes 24 microfarad. The value of K is. So here we are given that we are having two capacitors and they are connected in series. So let us consider we are having two capacitors C1 and C2. They are connected in series. Capacitance is same, which is over 40 microfarad. And we can say our C1 is equal to C and C2 is equal to C. But in one of the capacitor, a dielectric is introduced. So let us suppose on C2 we have introduced a dielectric. So C1 is going to have same capacitance, that C1 will be still equal to C, but capacitance of C2 is going to change. Let us suppose that is our C2 prime. This will be coming as K times C, and we have a dielectric constant K. And under this condition we are given that the equivalence capacitance is our 24 microfarad when it is having dielectric. So we can just use the equivalent capacitance formula. So you can say equivalent capacitance which is our 1 upon C equivalent will be equal to 1 upon C1 plus 1 upon C2 prime. And we already know our equivalent is our 24 microfarad is equal to C1 is equal to our C plus C2 prime is our K times C. We can take C as common, so this comes 1 upon C, 1 plus 1 upon K. C is given to us as 40, so this comes as 1 upon 40 microfarad, 1 plus 1 upon K. And now it is you can say I think much better is we do not take common, we leave it as it is. So this is 1 upon 40 and this comes as 40K. Therefore, we can write that 1 upon 40K will be equal to 1 upon 24 minus 1 upon 40. LCM we can get as 120 and this comes as 5 minus 3, which comes as 2 by 120. Therefore, we can write that the value of K will be equal to 1 upon 40 multiplied by 120 divided by 2. And 0 goes by 0 and this goes by 3. So we get that the value of K is equal to 3 by 2, which is 1.5. So option A is correct. Next question. We are given two electric dipoles of dipole moment 1.2 into 10 to the power minus 30 centimeter and 2.4 into 10 to the power minus 30 centimeter, I think. Yeah, is placed in two different uniform electric field of strength 5 into 10 to the power 4 Newton per coulomb and 15 into 10 to the power 4 Newton per coulomb respectively. The ratio of maximum torque experienced by electric dipoles will be 1 by x. The value of x is. So here we are having two dipoles. First dipole, let us call this as P1, having a dipole moment P1, which is our, I think this should be coulomb meter, not centimeter. Coulomb meter, and here also coulomb meter. So it will be our 1.2 into 10 to the power minus 30, and electric field, let us suppose that is our first E1 is given as 5 into 10 to the power 4. Similarly, for the second one, P2 is our 2.4 into 10 to the power minus 30, and we have our E2 is equal to 15 into 10 to the power 4. And the equation for the maximum torque that is our tau is equal to product of electric field and the dipole moment. We can divide this into tau 1 and tau 2. We can say our tau 1 is equal to, for the first one we substitute the value, we get this as 1.2 10 to the power minus 30. Electric field is our 5 into 10 to the power 4, which gives us 6 10 to the power minus 26. and tau 2 for the second one, that is our dipole moment E2 is equal to 2.4 into 10 to the power minus 30, 15 into 10 to the power 4, and this comes as 36 into 10 to the power minus 26, and we need to find out the ratio. Ratio is 1 upon x. Okay, so you can say our tau 2 upon tau 1, this will be coming as 36 into 10 to the power minus 26 divided by 6 into 10 to the power minus 26, and this goes by 6, which comes as 6 is equal to, we are given this as 1 upon x. 1 second. Maximum torque experienced by the electric dipoles will be, okay, and I think so from here we can say our x is equal to 1 by 6, and this is when I've taken the ratio of tau 2 by tau 1. Okay, if I reverse it, it will be coming as x, because in that case tau 1 upon tau 2, we are going to get this as 1 by 6, which is equal to 1 by x, and this will be giving me value of x equal to 6. Okay, so either it will be 1 by 6 or it will be 6. Next question. We are given a slab of dielectric constant K has the same cross-sectional area as the plates of parallel plate capacitor and thickness 3d by 4, where d is the separation of the plates. The capacitance of the capacitor when the slab is inserted between the plates will be, given that C0, capacitance of the capacitor with air as medium between the plates. So we are given that we have a parallel plate capacitor whose original capacitance is our C0, and d is the distance between the plates, A is the area. In this we have introduced a dielectric whose thickness is 3d by 4. So this thickness is our 3d by 4. So therefore the remaining portion is equal to d by 4, and dielectric constant is given as K. So this we can consider this is a C1 capacitor and this is a C2, because here only air is present. So we are having now two capacitors and they are connected in series. Okay, we can say we are having two capacitors. One is C1 and another one is our C2, and C2 is having a dielectric of constant K, and the thickness is our d by 4 and this is our 3d by 4. So we can write our C1 will be equal to epsilon A upon d by 4, and our C2 is equal to K epsilon A divided by 3d by 4. And both are in series, so we can write the equivalent capacitance 1 upon C is equal to 1 upon C1 plus 1 upon C2. And we simply substitute the values. Our 1 upon C, C1 is our, this will be our 4 epsilon naught A, and we have this as D, plus C2 will be our 4K epsilon naught A and 3D. So we can take common will be our D upon 4 epsilon naught A, and it comes as 1 plus 3 by K. And we can write, therefore our C will be equal to, this will be our 4 epsilon naught A, and this is our D multiplied by 1 upon 1 plus 3 by K. But the original capacitance is given as C0, and its value will be equal to, this will be C0. So this comes as our 4 times C0 and 1 upon 1 plus 3 by K. Okay. And we can just take LCM. We get this as C is equal to, this will be 4 times C0 K, and this will be our 3 plus K. So this will be our equivalent capacitance. This comes as 3K0, 3K0, 4K0, 4K0, 3 plus K. Option A is correct. Option A is correct. Next question. It states that two identical positive charge Q each are fixed at a distance 2a apart from each other. Another point charge Q0 with mass m is placed at midpoint between two fixed charges. For a small displacement along the line joining of the fixed charges, the charge Q0 execute SHM. The time period of oscillation of Q0 will be. So we are given that we are having two charges, and these are our, suppose this is our first charge plus Q, and this is also our plus Q, and the distance between them is our 2a, and let us suppose that this we consider at origin, and therefore we get one of the charge will be at a distance of a comma 0, and another one will be our plus a comma 0, and Q0 is placed at this particular point. This is our Q0. So it is at a distance of a respectively from each charge, and it is displaced by a small amount. Let us suppose that small amount is our x. So we can say that initially Q0 is at x equal to 0, and finally is displaced to x is equal to x. So therefore, with respect to our left charge, the distance will be coming as this distance will be coming as a plus x, and on the right side the distance will be coming as a minus x. Therefore we can say that from left charge distance is our a plus x, and from right charge we are having a distance which is our a minus x, and let us call this as our r1 and this is our r2. So we can find out the force due to left charge. Force due to left charge, let us call this as FL, will be equal to K Q times Q naught, and we have this is R1 square, and this can be written as that our F left will be equal to K Q naught, R1 is our A plus X whole square, and the direction will be towards right. Similarly, force due to right charge that is a FR will be equal to K Q times Q naught, and we have this is R2 square. So we get this as F right will be equal to K Q naught, and this is A minus X whole square, and its direction will be towards left. So net force, both the forces are opposite, therefore you can say net force, that is our F net, will be equal to left minus force right. We can take common will be our K Q naught, and this comes as A plus X whole square minus A minus X whole square. And we are going to use the binomial approximation. So you can say binomial approximation, which gives us that for x which is very small, smaller than a, we can write that 1 of plus minus x whole square can be written as 1 upon a square minus plus 2x upon a cube. Therefore, we can write our F net will be equal to K Q times Q naught, and this comes as 1 upon a square minus 2x upon a cube minus 1 upon a square plus 2x upon a cube. Obviously this term will be cancelling each other. Sorry, not this term, my mistake. The term a and a will be cancelling each other. Therefore, you can say our F net will be equal to, this comes as our minus K Q naught, and this will be our 4, and we have this as our a cube and times x. Obviously from here we can say our f net is equal to minus of kx. Let me write this as k prime in order to differentiate with this k. And so if you make a comparison, we can say our k prime will be equal to 4k q naught upon a cube. And time period will be equal to what t is equal to 2 pi square root of m divided by this is our k effective, and this k prime is nothing but our k effective. Therefore we substitute it, we get this as 2 pi, and square root of this will be coming as ma cube divided by 4k q naught. And the options, okay, we can substitute value of k, that is over 1 upon 4 pi epsilon naught. So we get time period t is equal to square root of, and we have this as 4q naught, and this is our k is 4 pi epsilon naught, so this comes as 4 pi epsilon naught times ma cube. They cancel the, okay, they are taken 2 pi inside. Let me also, so inside this will be multiplied by 4 pi square, and this 4 and 4 cancel out, so we get our time period will be equal to, we have this as 4 pi cube epsilon naught ma cube and q naught whole square, and we get this 4 pi cube ma cube, so option A is correct. Option A is correct. Next question. It states that a long cylindrical volume contains a uniformly distributed charge of density rho coulomb per meter cube. The electric field inside the cylindrical volume at a distance x is equal to 2 epsilon rho meter from its axis is. A basic figure is given to us. We have a cylinder of length L, and we are given that electric field we need to find out at a distance x, which is also given to us. Okay, so basically we are going to use Gauss law, find out the electric field, and then we can just equate them. So let us consider a Gaussian surface, and we have our cylinder. So this is our cylinder and the axis, and inside it we consider a cylindrical Gaussian surface. And the radius is our x, and suppose its length is h, and okay, so the electric field will be in same direction as that of our surface area, that is our ds. And we are basically interested in finding electric field, so we can use our Gauss law. Therefore we can say from Gauss law, electric field for a enclosed area will be equal to our Q enclosed upon epsilon naught. And we have considered a Gaussian surface of length h and distance of thickness we can say x. And here, because the electric field is in the radial direction, so therefore only the curved surface of this Gaussian or a cylinder is going to contribute toward our flux. Therefore we can say that flux through the Gaussian surface that is above phi will be equal to electric field multiplied by curved surface area. Curved surface area. So we substitute the value, we get our electric field is equal to our 2 pi x times h. And for finding out the charge enclosed, so you can say enclosed charge that is our Q enclosed will be equal to charge density multiplied by the volume, and we get this as charge enclosed will be equal to our pi r square h. So therefore through the Gauss law, which you can say equation 1, from equation 1 we can write electric field multiplied by 2 pi xh is equal to, and this is your rho pi r square h divided by epsilon naught, and pi h sorry, here it is not, it is x, and here also x, and x and this square cancel out. Therefore we get our electric field is equal to rho x divided by 2 epsilon naught, but we are given that our x is equal to, so we substitute value of x, we get this as rho 2 epsilon naught multiplied by x is given to us as 2 epsilon naught divided by rho, and they cancel out each other, which comes as 1 volt per meter. So it comes as 1 volt per meter. Next question. It states that a charge 4 coulomb is to be divided into 2. The distance between the two divided charge is constant. The magnitude of the divided charges so that the force between them is maximum will be. So we have to divide 4 coulomb into 2 parts. So let us consider that the total charge which is given to us as let us suppose that is our capital Q, and this is our 4 into 10 to the power minus 6, and it is divided into two parts. So let's divide into two parts. First part is our Q. Obviously second part will be coming as Q minus small q, and the distance between them is constant. Suppose r is the distance between the two. So we have to find out the value of q such that small q rather, because capital Q we know, we can just find out the other part also, that the force becomes maximum. So we can write value of the force, equation of the force will be equal to over k q capital Q minus small q divided by r square, and our r is fixed, so it means both k and this r square is constant, and we from here we can say our force is proportional to q minus small q, and we need to maximize our force. Okay. So we differentiate it with, for the sake of convenience, let us say this is equal to over capital Q times Q, and this comes as Q square. So we need to maximize this. So obviously we are going to find out its differentiation. So we can say our df upon dq will be our q minus 2q, and we are going to give it equal to 0. This gives us that small q is equal to capital Q by 2, and we can check if it is maximum or not. So we can say for maximum, double derivative which is coming as minus of 2 is less than 0. So obviously at this point the force is our maximum, and capital Q is given to us. Therefore we can say our small q will be equal to capital Q is 4 microcoulomb, so this comes as 2 microcoulomb. So both charges will be same, so it will be 2 microcoulomb as our q, and capital Q minus q is the other charge which will be also coming as 2 microcoulomb. So it will be 2 and 2 microcoulomb. Option B is correct. Next question. It states that as shown in the figure, in steady state, the charge stored in the capacitor is dash 10 to the power minus 6 coulombs. Basic figure is given to us. We have three arms which are parallel to each other, and we need to find out the charge stored in the capacitor at steady state. So we know at steady state capacitor is open circuit. At steady state capacitor is open circuit. So we can just redraw the circuit. So capacitor will be open circuit. So we are given this as 10, R is our 10 ohm, capital R is our 100 ohm. We have capacitor here, and we have here R prime which is given as 200 ohm. So as capacitor is open circuit, no current will be flowing in this capacitor arm. So if current flowing through here is I, so obviously through here will be also I. So we can easily find out the value of the current I. So we can say current I will be equal to our E divided by small r plus EMF divided by small r plus capital R, which is 10 divided by 10 plus 100. And if we see that the potential drop across this 100 ohm resistance is in parallel with the capacitor open circuit as well as R prime. So we need to find out our potential drop across our 100 ohm resistance, and this will be equal to our 110 and amperes. So we can find out the potential drop at resistance R. Potential, we can say voltage drop at R is equal to 100 ohm. So let us call this as V100, which will be equal to 10 and multiply by 100, and this gives us that of 100 ohm will be equal to our, this 10 and 10 goes away, this comes as 100 divided by 11 volts. Now this voltage drop will be in parallel with our, or we can say that voltage drop across capacitor C, let us call this as VC. Therefore voltage drop across capacitor, that VC will be equal to our V100 because they are in parallel, which will be our 100 divided by 11. Now we can easily find out the charge. So you can say charge on capacitor Q is equal to, we say that our capacitance multiplied by VC. So we get our Q is equal to, capacitance is given to us as 1.1 microfarad, 1.1 into 10 to the power minus 6, and this is our 100 divided by 11, and this comes as our 10 microfarad, or we can say 10 into 10 to the power minus 6, so which is equal to our 10 into 10 to the power minus 6. So here we are going to get as 10. So this is our 10. Next question. It states that a parallel plate capacitor with width V centimeter and length 8 centimeter, separation between the plates is 4 millimeter, is connected to a battery of 20 volt. A dielectric slab of dielectric constant 5 having length 1 centimeter, width 4 centimeter and thickness 4 millimeter is inserted between the plates of parallel plate capacitor. The electrostatic energy of this system will be, is given as dash epsilon naught. So we have to find out this missing value. And here we are given that initially we have a capacitor and a capacitor with the so we are given that the width of parallel plate capacitor is 4 centimeter. Okay, so we have, so this is our parallel plate capacitor, and we are given that its width is, plate width is 4 centimeter and the length is 8 centimeter, and the distance between the plates is 4 millimeter. Connected to a battery of 20 volt, and then we have a dielectric constant, and let me draw it here now 1D because we can just find out area with respect to this. And dielectric constant is having a length of 1 centimeter and width is 4 thickness is 4 millimeter, width is 4 centimeter. Okay, so we have our dielectric, that is something like a cuboid, like this, and it is introduced between the plates. And so these are the plates of the capacitor, and thickness is 4 millimeter, so it is going to fit entirely inside this one. This is about 4 millimeter, and we have its length is 1 centimeter and width is 4 centimeter. Okay, so this will be our 1 centimeter and width will be our 4 centimeter. This portion will be about 4 centimeter. And it is still connected to a battery source. Battery source is not removed, so the voltage will be constant. So therefore we can write that, first of all, let us discuss only the parallel plate capacitor. So we have a capacitor plate dimensions. We are given that the width W is our 4 centimeter, which will be our 0.04 meter, and we have length is our 8 centimeter, which will be our 0.08 meter, and we are having plate separation which is basically our D is equal to 4 millimeter, that is 0.004 meters. Battery voltage is given as 20, that is common. Now we can dielectric slab. So dielectric slab, dielectric constant is given as 5 and its length L is given as 1 centimeter, which is 0.01 meter. Width is our 4 centimeter, which is our 0.04 meter, and the thickness is our 4 millimeter, which is our 0.004 meter, and that is equal to D. And in the first case, we can find out the area. So area will be equal to W multiplied by length L, which will be coming as 0.04 and 0.08, giving us 0.0032 meter square. And its capacitance can be written as our epsilon naught A upon D. Let us call it as C naught. And the area of the dielectric let us call this AD, will be equal to, we have this 0.01 multiplied by 0.04. This gives us that our AD will be equal to 0.004 meter square. So therefore, the rest of the area means this particular area, this is without dielectric. So we found out this area. So we are going to find out this area without dielectric. So area without dielectric that will be having area of air will be equal to area of the capacitor minus area of the dielectric. So we get area of the capacitor, which is consisting of only air, will be equal to 0.0032 minus 0.004, which comes as 0.0028 meter square. So we have two capacitors. We can just draw the approximate figure for that. One capacitor is having dielectric, and other capacitor is having simply air. The width of them is same, but area is different. So this is our AD and this is our A air, and they are connected with a voltage source of V. And let us call this as its capacitance as C air, and this as C dielectric. Therefore, we can say that our capacitance of air part that is our C air will be equal to epsilon naught area of the air and divided by D. We substitute the value, we get CA will be equal to our epsilon naught. A air we found out as 0.0028 and distance is our 0.004. This comes as 0.7 epsilon naught. Similarly, we find out capacitance of dielectric part. capacitance of dielectric part, which is our CD, will be equal to K epsilon naught area of the dielectric, and distance between them is same. K is given to us as 5. This comes epsilon naught area of dielectric is 0.004 divided by 0.004. 1 0 is missing. This comes as 0.5 times epsilon naught. So total capacitance, as they are in parallel, so you can say total capacitance C will be equal to our C of air and C of dielectric, which comes as 0.5 plus 0.7 epsilon naught. So we get C is equal to 1.2 times epsilon naught. And we are supposed to find out energy of the system. And they are connected to the voltage source V. Therefore, you can say energy E is equal to half CV square. This comes as half 1.2 multiplied by 10 is, sorry, I think 10, 20, 20. 20 whole square, and this comes as 240 epsilon naught times joule, and we are given this will be dash epsilon naught, so the value of dash is 240. So we get this as 240. Next question. The total charge in system of capacitance C1, C2, C3 and C4 connected in parallel, assumed to a battery of 20 volt, is connected to the combination is. So we have 4 capacitors. So this is our C1, C2, C3, C4, and all these are connected in parallel with a voltage source, let us suppose V. So we are going to find out equivalent capacitance of these all the 4 capacitors. So we can say equivalent capacitance which is our C is equal to C1 plus C2 plus C3 and plus C4. We substitute the values. We are given this is 1, 2, 4 and 3. 1 plus 2 plus 3 plus 4 microfarad. So we get our C is equal to 10 microfarad. So therefore we can just draw equivalent part. So we have one capacitance C and connected with a voltage battery source of 20, and we need to find out the total charge. So you can say from here that the total charge Q will be equal to C times V. So Q is equal to C is our 10 into 10 to the power minus 6, voltage is our 20, so this comes as 200 microcoulomb. So option number A is correct. A is correct. Next question. we are given that a composite parallel plate capacitor is made up of two different dielectric materials with different thickness T1 and T2 as shown in figure. The two different dielectric materials are separated by a conducting coil F. The voltage of the conducting coil is dash volt. So we are given this basic circuit having two capacitances. Let me draw it a little bit on a larger scale. So this is our first capacitor, and in between we have a foil, and on the lower side there is our second plate, that is second capacitor. We are given that this is our ER1 is our 3 and its thickness is given as 0.5, and its ER2 is given as 4 and its thickness is given as 1 millimeter, and it is connected with a battery source of 100 volt. So we have to keep in mind that the net voltage or total voltage across this combination which should be always 100 volt. It has to be 100 volt. And for the first one, let us call this capacitance as C1. For the second one, we call this as C2. So we can say our C1 will be equal to we are given as ER1 E naught A divided by D1. Area will be same, and this comes as our 3 epsilon naught A, and it is 0.005. Sorry, it is in millimeter. So 1 extra 0. 5. Similarly, we can write for C2 will be equal to ER2 epsilon naught A upon this is D1 and this is D2, and this is given as 4 epsilon naught A divided by D2 is our point this is about 1 millimeter, so it will be coming as 0.001. Now we can easily find out the equivalent capacitance. Equivalent capacitance 1 upon C is equal to 1 upon C1 plus 1 upon C2, and we substitute value of our C1 and C2. We get this as 1 upon C equivalent is equal to, and C1 is our 0.0005 3 epsilon naught A plus this is our 4 epsilon naught A, and this comes as 0.001, and this will be coming equal to as 0.005 divided by 12 epsilon naught A. So we can write our C equivalent will be equal to 12 epsilon naught A upon 0.005, which can be written as 2400 epsilon naught times A, and it is connected to a battery of 100 volt. So therefore we can say charge on the system. Charge on the system, that is our Q is equal to our C equivalent multiplied by supply voltage, that is a battery voltage, V given as 100. So we find out our Q is equal to, this is our 2400 multiplied by 100, So this comes as 24 into 10 to the power 4. Epsilon naught times A. So this is the charge. And based on this charge, because this will be net charge on the capacitors, and we easily can find out the potential difference across each capacitor. Potential difference across each capacitor, because capacitors are connected in series, so the charge will be same. So we can say potential difference across each capacitor, which is the general formula is about V is equal to Q upon C. So we can say for C1, we can write that our V1 will be equal to Q divided by C1. Q is our 24 into 10 to the power 4 epsilon naught A divided by this comes as our C1 will be equal to our C1. Okay, C1 will be equal to our 6000 epsilon naught A, and our C2 will be equal to our 4000 epsilon naught A. So C1 is our 6000, so this comes as 6000 epsilon naught A, and epsilon naught A goes away, so we have here 3 zeros, so 3 is cancelled with 4, so we are left with here, and this goes by 4, this comes as 40 volts. Similarly for C2, V2 will be equal to our Q divided by C2. We get this as 24 into 10 to the power 4 epsilon naught A, and here we have our 4000 epsilon naught A. Once again this goes by 6, giving us 60 volt. And so we found out that the potential difference across each capacitor is, not each capacitor, yeah, C1 is 40 and C2 is 60. Okay. So we can say that we have our C1, and here we have V1 is equal to 40, and we have a C2 with V2 as our 60, and the foil is in between, so this is our foil. Now we need to find out the potential, and here 60 plus 40 gives us that the potential, total net potential difference is equal to 100. So if we assume that lower plate of the C2 is our 0 volt or connected to ground, from the figure also we can see that this potential, this plate is connected to the our negative part of the supply. Okay. So therefore this will be 0, and automatically we are going to get this as our foil is going to have a potential of our 60 volt. So we can say that if bottom plate of C2 is at 0 volt, then voltage of the foil will be equal to 60 volt. Therefore is our 60 volt. Next question. It states that two uniformly charged spherical conductors A and B of radii 5 mm and 10 mm are separated by a distance of 2 cm. If the spheres are connected by a conducting wire, then in equilibrium condition, the ratio of magnitude of electric fields at the surface of the sphere A and B will be. So we are given two spheres A and B. So this is our A and this is our B sphere, and they are connected with a wire, and in equilibrium we have to suppose, let us suppose here electric field is our EA and here the electric field at EB, and its radius is suppose our RA and its radius is our RB. So as they will be connected by a conducting wire, they should be having the same potential in electrostatic equilibrium. So you can say when two conductors are connected they come to the same potential, in electrostatic equilibrium. And we know that the electric potential at the surface of sphere radius r, the formula is given as V is equal to K times Q upon R, where Q is the charge on the sphere, and the electric field at the surface E will be equal to 1 upon, let me write it K only, K is equal to Q upon R square. So we can divide, we have two spheres rather, let us call this as RA is about 5 mm, which will be coming as 0.005 meter, and we have our RB which is our 10 mm coming as 0.01 meters. So they are connected with wire, and the potential, let us suppose, is VA and VB, which will be equal. Therefore we can say that VA is equal to VB, which gives us our QA upon RA is equal to QB upon RB. And this gives us that QA upon QB is equal to RA upon RB, which comes as 5.10 is equal to 1 by 2. Similarly, we can find out their ratio of their electric field. EA upon EB will be equal to QA upon RA square, QB upon RB square. This comes as QA upon QB times RB square upon RA square. Now we simply substitute value. QA, QB we found out is 1 by 2, and we get this as our RB is our 10 upon 5 whole square, and this goes by 2, so this comes as 4 by 2 giving us 2. Therefore, this is our ratio of electric field EA upon EB. So the answer is 2:1. Option B is correct. B is correct. Next question. It states that a source of potential difference V is connected to the combination of two identical capacitors as shown in the figure. When K is closed, the total energy stored across the combination is even. When key K is opened and dielectric constant 5 is introduced between the plates of capacitors, the total energy stored across the combination is now E2. The ratio of E1 and E2 will be. So in the first case, we are given that the key is closed. So we can say when key is closed, both the capacitors are in parallel. Therefore, we can say our, let us call this as C1 and we call this as C2. So we can say C1 and C2 are in parallel. Therefore, we can find out a C equivalent will be C1 plus C2, which is C plus C is equal to over 2C. And now we can just draw the equivalent circuit. We have a voltage source of V, and we found out the equivalent capacitance is our C equivalent. So we can find out the energy E1 will be equal to our half C equivalent V square, and C equivalent is over 2C, so this comes half 2C V square. This gives us that our E1, 2 and 2 cancel out, this gives us CV square. Now in the second case, the key is opened. Key is opened and dielectric is introduced, and dielectric is introduced. So when key is opened, the circuit becomes like this. this is a voltage source V, and we can say that, let us call this as capacitance as C1 prime because of the dielectric, and this is our C2 prime also because of the dielectric. It is having same dielectric constant K. So from the figure we can clearly see that this capacitor is having the same voltage, that is V, voltage connected to the capacitor, but our C2 is going to have same charge. So this is going to have same potential, and this is going to have same charge. So we can say that our C1 prime will be equal to our K times C1. K is our 5 and C1 is our C. And for our C2 prime will be also equal to K times C2, which gives us 5C. And we can find out the charge on this. Okay, we need to find out energy. So we can say total energy E2 will be equal to energy on our C1 prime plus energy of the C2 prime. C1 prime is having same potential, so we can say half, and this will be C1 prime V square, and plus it is having same charge, so this comes half Q square upon C2 prime. And the initial charge on this, because it is a voltage source V, so charge here will be our C times V. And we substitute the value, we get our E2 will be equal to half, this comes as 5 times C V square plus half, here we have CV whole square because charge is going to remain conserved. So C2 prime is 5 times C. And we can just write it now, 5 by 2 CV square plus half, this comes as C square V square by C. So this comes as also CV. One second. Okay, values are not given to. So this comes as C square and V square, so this comes as C square and this comes as 1 by 10. So we can take CV square as common, and this will be coming as 5 by 2 plus 1 by 10, and 10 will be our LCM, so this comes as CV square and we have 10, this comes as 25, yeah, 25 plus 1, that is 26, and we can cancel it by 13 and this by 5. So we get our E2 will be equal to 13 by 5 times CV square, and our CV square is nothing but our EV. So here we can substitute our, so not EV but E1, so this comes as 13 by 5 times E1. So we get ratio of E1 by E2 will be equal to our 5 by 13. So option C is correct. Next question. We are given 3-point charges of magnitude 5 microcoulomb, 0.16 microcoulomb and 0.3 microcoulomb are located at the vertices A, B, C of a right angle triangle whose sides AB is 3 cm, BC is 3 square root of 2 cm and CA is 3 cm. And point A is at right angle corner. Charge at point A experiences dash Newton of electrostatic force due to the other two charges. Okay, we can just draw an approximate figure for that. 90-degree angle is given as at C. So, 90 degree is given as A. So this is our A, and let us suppose this is our C and this is our B. A and B is given as 3 cm. A and C is also given as 3. B and C is given as 3 root 2. So force of charge B on A, let us call this as our FBA, and force on charge C on charge A, let us call this FCA, because all are positive, so they will be repelling each other. So we can easily find out our both the forces, and so our FBA will be equal to our K into charge at A, charge at B, and distance is same, so we can just assume this is also R and this is also R square. So we get this 9 into 10 to the power 9. QA is our 5 into 10 to the power minus 6 and 0.16 into 10 to the power minus 6. It is 3 millimeter, 3 centimeter, and also centimeter. So it comes at 0.03 whole square. So we get our FBA will be equal to 8 Newton. Similarly, we can find out our FCA will be K multiplied by QA, QC and radius square. 9 into 10 to the power 9, and we have this as 5 into 10 to the power minus 6 into 0.3 into 10 to the power minus 6 divided by 0.03 whole square. So we get this as FCA will be equal to 15 Newton. Therefore, we need to find out the net force on A. Net force on charge at A. So we are having this here charge A. This is our FBC, and this is having our FCA. So the resultant will be something like this. So this is our F net. So you can say our F net will be equal to FBC square plus FCA square and its square root it is 8 plus 15. So we get this as 8 square plus 15 square, and it is a 64 plus 225. 64 plus 225 and its square root, giving us our net force F net will be equal to square root of 289, which gives us 17 Newton. So we have a force of 17 Newton. So this completes part 1 for the year of the question which were asked in the year 2022. In this part 1 we solved 14 questions, and all these, sorry, not 14, I think it was 17. Yeah, we solved 17 questions, and remaining questions we will try to cover in next 3 parts, hopefully covering the mains as well as the advanced part. So in the part 1 we completed our 17 questions. So this complete all the 17 questions from the year 2022 as a part 1. Thank you.